Hello. In this part of the lecture, we're going to look at another circuit analysis technique called superposition. I will first go over some key properties of this technique, and then we will look at the general problem-solving procedure to understand how we can use this technique to solve for the parameter of interest. So superposition is generally used in circuits dealing with multiple sources. For example, if we have two voltage sources, two current sources, or one voltage source and one current source, and so on. Because the voltage source, current source, and the RLC components we are dealing with in this course are perfectly linear, we can simply perform a summation or linear addition in the analysis. To perform this technique, what we have to do is we analyze the circuit by activating or turning on one source at a time while keeping the other sources off. So as an example, if we have three voltage sources, so what I have to do here, so if I call them V1, V2, and V3, so what I have to do here is I need to keep the first one, the V1 source on, while deactivating V2 and V3. And then I move on to the second voltage source, V2. I keep that voltage source on while deactivating or turning off V1 and V3. And I'll do exactly the same to the last one. So once I have stepped through all three sources, in this case is the voltage source, you can also do the same for the current source. So once I have stepped through all three sources, then to find the target parameter, right, it can be either voltage or current, all I have to do is I sum up the contributions due to each source, and then I'm done. So then the question is, how do I go about turning off the sources, right? So I can have, again, a voltage source and a current source, okay? So to turn off the current source, all you have to do here is you set this current I to 0. Right? So this is my current source here, and I zero out, okay? I set this current source to 0, okay? And correspondingly, I have to find the resistance associated with this current source. So how do I go about finding this resistance? Well, we know R is equal to V over I. And if I were to set this I to 0, okay, so the bottom here is set to 0, then the corresponding resistance in this case is going to be infinitely large. Right? So in other words, the resistance associated with a current source that is set to 0 is equivalent to having an open circuit. Right? So when R is equal to infinity, this is as if the circuit is open. Right? This current source is open. So if I were to deactivate, okay, in other words, if I were to turn off this current source, all I have to do is I set this current source to open. Okay, I cross it out. Okay, but the way you will go about justifying why this becomes an open is by following this procedure. And so we talked about, we learned about this Ohm's law, right? So R is equal to V over I. So when I is 0 out, is set to 0, then V divided by 0 will give you something very, very large, infinitely large, which is equivalent to an open circuit. Okay, so to deactivate this current source, all you have to do is you zero it out. You set it to an open circuit. You zero out the current. Okay, so for the voltage source, okay, I'm going to do the same thing here. Right? I'll follow the exact same procedure. I'm going to zero out this voltage. I set the V to 0. I set the V to 0. And I'm still going to use this Ohm's law, right? So when V is set to 0, so R is equal to V over I. When V is set to 0, so the corresponding resistance associated with this voltage source becomes 0, right? Which is equivalent to a short. So in other words, if I were to deactivate a voltage source, I can simply short out this voltage source. I can replace it with a wire, shorting these 2 points. So to deactivate a current source, I can cross this current source out because I know that the resistance associated with this current source becomes very, very large. While the opposite is true for the voltage source. When I deactivate a voltage source, I set this voltage to 0. The corresponding resistance associated with this voltage source becomes very, very small, equivalent to a short. So I have both ends of the spectrum, right? So I have an open for this current source when it's deactivated, and I have a short for this voltage source when it's deactivated. So now we know how to turn off or deactivate the sources. Then the next thing is we will need to calculate or evaluate the parameter of interest, right? And this parameter of interest can be either a voltage drop across a resistor or a current flowing through a resistor and so forth, depending on the question, depending on the circuit that you need to analyze. And then finally, the very last step here, this is sort of a very straightforward step. If you know how to deactivate the sources and you find the contribution due to each source, and all you have to do at the very last step is you sum up the contribution due to each source. Okay, so if I have, let's say, 5 voltage sources, then obviously you will have to sum up all 5 contributions, right? Then equivalently you have 5 terms, okay, that you need to sum up. Okay, and if you have 3 sources, then you will have 3 terms that you need to sum up linearly. Okay, it's a linear addition, right, which gives rise to this superposition. Okay, so I'm going to already go to my first example, and I'm going to show you how you can find the unknown voltage using superposition. But before that, I wanted to use this example here, and I'm going to use nodal analysis to sort of set a reference, right, to understand, let's say if we were to use just the nodal analysis, can we still get the answer that we want? And then we compare that with the superposition technique. Okay, and obviously, if you do everything right, the answer is yes. Okay, but I wanted to first show you how we can use nodal analysis to solve this problem. So here is what I have in the circuit. So the variable of interest or the parameter of interest is the voltage drop across this 4 ohm resistor, which is labeled as Vx. And this Vx is the same as this voltage between this node and the ground, right? I notice that I have a reference node, which is my ground in this case. And as well, you see that I have 2 sources, 1 voltage source and 1 current source. Okay, and of course, the circuit, depending on the circuit given to you, it can be more complex, right? Involving, let's say, 3 sources, as you will see in one of the examples later on. Okay. So let's say if I only have 2 sources, so I have 6 volts on the left and 3 amps on the right. And by using nodal analysis, I wanted to find this voltage Vx, which is the voltage drop across 4 ohm resistor. So I'm going to just simply use nodal analysis. So I take this voltage Vx minus 6 volts, right? Because I wanted to find what is the current flowing out of this node. So I take Vx minus 6 divided by 8. Okay, so that's the current flowing out of this Vx going to the left. The current going down this way is simply Vx minus 0, right? Because I have a reference node which is grounded. Okay, so I set it to ground. So Vx minus 0 divided by 4. Okay, so there's this term here and also this term. Okay. And then the last one is the current flowing out, right? But we know that the current flowing out, right, is equal to minus 3 in this case. So if I move it to the other side of the equal sign, I have plus 3. Okay. So everything checks, right? So in other words, current going in has to be equal to current going out, right? The sum, algebraic sum of current, okay, going into a node has to be equal to the algebraic sum of the current leaving that node. Okay, so then the rest is about finding this Vx, right? So I solve for this Vx from this equation, then I know that this Vx is simply equal to 10 volts. Okay. So the next thing I wanted to do here is I wanted to use superposition to find the same variable based on the same circuit. Okay. So it's the same circuit here, and it's the same Vx that I need to find using superposition. So first of all, I'm gonna zoom out a little. Okay, so it's the same circuit here, copy and paste, right? So as a very first step, remember I need to deactivate the source. And we have two sources here. So I have 6 volts and 3 amps. Right? So the first source that I'm going to deactivate here is this 3 amp current source. And as you may recall, to deactivate this current source, all I have to do is I set this current to 0. Okay, so let's quickly go back to this page here. So current source is deactivated when you set this current I to 0. Okay, and the corresponding resistance associated with this current, which is now deactivated, is equivalent to an open circuit, right? As I've shown you earlier, right? So we simply just use this Ohm's law to determine what is the resistance associated with this source. So for current source, we know it becomes an open. So knowing that, all I have to do here is I just simply cross out this current source, right? So that's why over here, this current source is gone and is now replaced by an open circuit. Open circuit, as we know, is basically not connected to anything. It's basically flowing. Nothing is connected. Okay, there's a huge resistance or impedance. Okay, and the rest of the circuit remains the same. So I still have 6 volts, 8 ohm, 4 ohm, and this is still Vx that I needed to find. Okay. So then the next step here is I need to evaluate, right? Remember, I wanted to find the target parameter based on this setup when only one source, okay, is on while the others are off. And since I only have 2 sources, I keep this one on and I deactivate the other one. Okay, so I label this Vx with a subscript I or 1. Okay, so Vx comma 1 to indicate that this is the parameter due to this 6 volt source. Okay, so Vx comma 1, okay, is equal to, right? So now I just need to perform a simple voltage division to find this Vx, right? So Vx is the voltage drop across 4 ohm here. And so I have to, so this is 6 times 4, right? 4 over the sum. Simple voltage division, 4 divided by 12. And that gives me 2 volts. Okay. But we are not done yet, right? Because we just, we would just look at one of the 2 sources. We still need to deal with the other one. Okay. So to deal with the other one, right, remember, so now I have to deactivate this 6 volt source while keeping this 3 amp current source on. Okay, so in other words, I activate this 3 amp while deactivating the other ones. Okay, so I keep this 3 amp, I need to deactivate, okay, deactivate this 6 volt. Okay. So how do I go about deactivating the voltage source? Well, so if we go back to this procedure here, so a voltage source becomes a short, okay, when it's deactivated, right? And remember, so all I have to do here, I set this voltage V to 0, okay? So when V is set to 0, I wanted to find the corresponding resistance, so 0 divided by I, right, whatever that I is, right? So because I have 0 on the top, so this resistance becomes 0, okay? It's equivalent to a short. So voltage source can now be replaced by a short circuit, simply. So if I go to the second step, deactivate the voltage source. Okay. So now if I flip it, right? So now I deactivate this 6 volts by presenting with a short, and I keep this 3 amp current source on. Okay. So, and then if I flip it, if I mirror about the y-axis, so now my current source is on the left. Okay. And this is still my Vx. Okay. Which is the voltage drop across this 4 ohm resistor, and then I still have the 8 ohm here. And remember, this short here, right, is because of the deactivation of the voltage source. Okay, because now the 6 volts voltage source is gone, replaced by a short now. Okay. Okay. So the next step is to find Vx. Okay. So, and I'm going to label it as Vx, 2. Right. Remember, we found Vx, 1, and Vx, 1 is coming from the first step, right, by deactivating the current source. Okay, by deactivating the current source. And then the second step is we need to deactivate the voltage source, which I call the parameter Vx, 2. Okay, so to find this Vx, 2, the strategy here is I first find a current passing through this resistor, this 4 ohm resistor, and I take that current multiplied by that 4 ohm resistor to find the voltage drop. Okay, so it's sort of a two-step process, right? So first of all, I'm going to find this Ix, the current flowing through this 4 ohm, and then I take that current multiplied by 4, right? So I times R, that will give you the voltage. Okay. So then the question is, how do I find this current passing through this 4 ohm resistor? Well, so this is straightforward because we learned about this current division technique back in last lecture, right? So this Ix simply, right? So I have 2 branches. I have 8 ohm and I have 4 ohm, okay? And remember, current likes to flow through the path with the lower resistance or the least resistance, okay? So I'm going to use this trick, okay? So Ix is equal to 3M multiplied by, since I'm looking at the current flowing through this 4 ohm, okay, so I need to take the resistance of the other branch, okay, and put it on the top, okay. So it's 8 ohm on the top divided by the sum. Okay, so if you recall this technique that we discussed in the last lecture, right? So 3 times 8 over 12, and that'll give you 2M. And 2M will be the current passing through this 4 ohm resistor. So knowing this current, so all I have to do is I take this current times R, so 2 times 4, right, 4 ohm resistor, that will give you 8 volts. Okay, so in other words, Vx, 2, right, contribution due to this current source, okay, is equal to 8 volts. Okay, so we have Vx, 2 from step 2 and Vx, 1 from step 1. Okay, so this is Vx, 1. Okay, so we have 2 contributions, right? And we know there are 2 contributions because we have 2 sources, 1 voltage source and 1 current source. Okay, so and this is one way you can perform your sanity check, right? By looking at the number of sources. If you have 10 sources, then you expect to have 10 terms like this, right? You have 10 contributions, Vx1 all the way to Vx10. Okay, as an example, right? So in this case, you know, we just looking at 2 sources, and if you follow the steps, right, so you know how to deactivate the voltage source and the current source, then you can find the target parameter quite easily. And typically, you can use simple voltage division and current division to find these unknowns Vx. Okay. All right. And as a very last step, right, and which is also a very critical step, is that superposition, as the name suggests, right, we need to perform this linear addition of these parameters. Okay, so V total, okay, V total is equal to the sum, okay, summation of Vx, 1, okay, and then Vx, 2, right? So this is 2 volts, and then this is 8, so that will give us 10. Okay, And let's quickly go back to the last page where we use nodal analysis to solve for this circuit. So Vx turns out to be 10, right? So the Vx is 10, as we found earlier, and we know that both techniques work. Okay, so superposition obviously can also be used for you to find this unknown voltage Vx. Okay, and you get the same answer. Okay, so let's look at the next example. So this example is slightly more involved, given that there are 3 sources instead of 2. Okay, and we have 2 voltage sources and 1 current source. Okay. So let's look at the first step here. So we have 3 sources here. So the first step that I did here is to only activate the 24 volt while deactivating the other 2. Okay. So I keep this one on and I deactivate the other 2. And as you recall, to deactivate a current source, all I have to do is I cross out this current source so that it now becomes an open circuit. The opposite is true when I have to deactivate the voltage source, right? So over there, I short that voltage source. Okay, I set that voltage source to 0 such that it now becomes a very low impedance, like a short. Okay, so if I sketch my equivalent circuit, okay, again, by incorporating this deactivation, so now this 4 amp current source is gone, right? So I don't have anything attached to over here, okay? And the 38 volt voltage source is also shorted out, right? So now I have this 4 ohm resistor directly connected to this here. I can assign the reference ground here, okay? Connected to the reference ground. Okay. Okay, so then the next step is to find the voltage across this 5 ohm resistor, right? So this is, remember I have the plus sign here and minus sign. This is the polarity specified as part of this example. Okay, so I wanted to find the voltage drop across this 5 ohm resistor with a plus sign on the left and minus sign on the right. Okay, so let's talk about the general strategy, how we can go about finding this V out, right, or VO. So the general strategy goes something like this. So in order for me to find this voltage here, okay, I'm going to first find an intermediate node voltage. And that intermediate node voltage is going to sit over here, okay, which I'm going to call it Vx. Okay, you can call it VA or VY, your choice, right? But let's just say Vx over here. Okay. All right, and then after finding this Vx, okay, if I know how to find this Vx, all I have to do is I perform another voltage division. Okay, I perform another voltage division so that I can find the voltage drop across this 5 ohm resistor. Okay, so the first voltage division allows me to find the voltage sitting at this node Vx. Okay, and then I perform voltage division again to find the voltage drop across this 5 ohm resistor. Okay, so I'm going to switch over to my one node here, and then I'm going to show you how you can perform this voltage division. Okay, so this is a snapshot of what we just saw in the notes. So I'm going to look at this node first, and I'm going to call it Vx. Okay, I'm going to find this Vx first. Okay. So how do I find this V? Well, so I know that this is 4, this is 12, right? So I can first combine the 4 and the 12 together, right? Because I know immediately they are in parallel, okay? So every time when you see an opportunity of simplifying your circuit, you always want to do that first, right? So you're going to combine 12 and 4, right? So 12 in parallel with 4 will give you 3, okay? So if I were to redraw my schematic or circuit, okay, it's going to look something like this. So now I have 3 here, I have 5, and this is plus on the left, the out, and then this is minus. This is 3, this is 6, and this is 24. Okay, but remember, our goal is still to find this Vx, right? So this is the kind of the intermediate node voltage that I wanted to find first, so that I can find the VO, okay, eventually. Okay, so how do you find this Vx? Well, I'm going to simplify this in such a way that if I can simplify my circuit, okay, into something like this, where I only have 2 components, right? So this here is still 24, right? So if I can simplify the circuit down to something like this, where I only have 2 components, 6 ohm, okay, and another resistance sitting over here, whatever that resistance is, then that means I can find this Vx easily, right? So in other words, I'm just going to call this Rx, okay? So Vx is equal to 24 times Rx over the sum, right? So if I can find Vx, then I can perform this voltage division very easily, right? Because it all comes down to just dealing with 2 resistive components and the voltage source, right? So we know how to do this very well, right? Rx over the sum, okay? But then the question is, what is Rx in this context, right? Okay, so Rx in this context is equal to, right? Remember, this branch here on the left, on the right, okay, it consists of a series combination of 5 and 3, okay? 5 and 3 ohm resistors, okay? So I can actually combine them first, right? 5 plus 3 will give you 8, okay? So that's the first step, right? So 5 plus 3 will give you 8, and that 8 ohm resistor can also be combined with this 3 ohm resistor such that I will just get 1 resistor altogether, right? Which I call Rx, okay? So if you want, you can say I have 8 ohm, right, which is 5 plus 3, okay? And then I have 3 ohm, right? This is coming from this 3 ohm here. And then I have 6 ohm, and I have 24 volts, right? So this 5 plus 3 is coming from 5 plus 3, right? That'll give you 8, so 8 ohm, right? And this 3 ohm and the 8 ohm can also be combined, right? Because we know they're in parallel, okay? So then the question is, what is Rx? Well, Rx simply is 5 plus 3 in parallel with 3 again, right? So 8 in parallel with 3. And that is my Rx, okay? So if you put this here and here, okay, then you're going to find this no voltage Vx, okay, which is the voltage drop between this node and the ground, okay? So if I go back to the circuit here, between this node and my ground, okay, this Vx is simply captured by the first term over here in the lecture notes. Okay? So I have 8 in parallel 3 divided by the sum, right? So 8, this is 8 in parallel 3, okay, divided by 6 plus the same term again, right? Again, this is 8 in parallel 3, right? 8 in parallel 3 on the top divided by 8 in parallel 3 plus 6 on the bottom, okay? And this term will give you Vx. Okay, so that's the first step. But we are not done, right? Because, eventually the parameter of interest is really this V out or VO, and which is the voltage across 5 ohm resistor. So what do we do here? Well, we just do another voltage division. So we have Vx, right? So we have Vx here, and I'm going to take this Vx, and then I do another voltage division. So I have phi over the sum, right? And the reason phi is on the top is because we wanted to find the voltage drop across 5 ohm resistor, not 3 ohm resistor. Okay, it's a 5 ohm resistor, so we put that on the top over the sum. So phi put on the top divided by the sum times Vx, right? Because Vx is this voltage over here, right? This voltage. Okay. So Vx times phi over the sum, so we will get the V out. Okay. So that's the second term over here. Okay. So when you work out the number, you will get 4 volts for the V out, right? And notice that this is VO1 or VO comma 1, right? Because 1 indicates that this is only coming from the first source. Okay, so we have 3 sources, and this is the contribution due to the first source. Okay. All right. So now let me go back to the lecture notes. Okay. So again, there's a two-parter, 2 terms. So this term accounts for Vx, and then the last term here accounts for this the voltage division one more time for you to get to this V out. Okay. So you ended up with 4 volts. Okay, so that's the contribution due to the 24 volt. So how about the contribution due to the 38 volt? Well, so if you look at the this circuit, right? This circuit sort of looks rather symmetrically, right? So even though the component values are not the same, but if you look at the way the voltage source or the sources are placed, right? So we have 2 sources, one on the left and one on the right, right? And then in the middle, we have this resistor here, and then of course we have this current source, right? So if you look at the way this circuit is set up, right? This is rather symmetrical. So that tells you that we can use the same technique, okay, to find this VO2, okay, when the 38 volt is activated. Okay, right. So again, if we keep this 38 volt here and we deactivate this voltage source and this current source, right? This current source will be open, and then this voltage source will be shorted out. Okay, so this now is shorted out. Then we only have this 38 volt activated. Okay, so this guy here is now active, and now we need to find the VO2, okay, due to the contribution of this 38 volt. Okay, but notice that, this VO2, right, is specified with a certain polarity, plus on the left and minus on the right, right? It's still the same as the first case, right? Because I need to follow this specified polarity, right? I cannot change the polarity arbitrarily, right? I have to follow it, okay? So now, when you work it out, okay, and I'm going to invite you to try it out on your own, right? It's exactly the same strategy, same technique. You perform the voltage division twice, okay? First, you land it over here, okay, and then you do another voltage division to find the voltage drop across this 5 ohm resistor. But now, the subtle difference here is that notice I have a negative sign, and that negative sign comes from the fact that now I'm driving from the right, okay, not from the left, okay. So, and the sign that you see first is the negative sign, not the positive, right? So when I drive this circuit with this 24 volts, I see the plus sign first on the left, okay? But when I drive this circuit from the right, the first sign that I see is negative, okay? So this is one way you can tell that there is a sign polarity difference, okay? There's a sign change, okay? But of course, you know, when you do the actual voltage division, you work it out, right? You'll see this quite easily as well. Okay, so I invite you to verify this later. Okay, just to make sure that you can first perform this voltage division. Okay, actually do it twice. Okay, to find this VO2, and at the same time recognizing that there is a negative sign along with this voltage. Okay. All right, so then the last step, right? So again, we have three sources, so that means, you know, we need to do this 3 times, okay? So the last source is the current source, so we need to keep this current source on while deactivating the other 2, okay? So to deactivating the other 2 sources, right, especially they're the 2 voltage sources, 2 sources of the same type, we simply just short the voltage sources, okay? And we keep this guy on, okay? We keep the 4N active. The rest remains the same, right? So we have 3 ohm, 6 ohm, 12 ohm, 4 ohm, right? Let's quickly check. You short this guy, you short this guy, so we have 3, 6, and then we have 12 and 4, okay? And we have 5 ohm over here, which remains in the same position, same location. Plus on the left, minus on the right, okay? Still 5 ohm. And then the current source is going to the to the left, okay? Okay, all right, so as a reminder, right? So every time when you see an opportunity of simplifying the circuit, you always want to do that first. Okay? So I know that this is 6 ohm and 3 ohm, right? I do see that they're in parallel, so I can combine them first. So 6 in parallel 3 will give you 2. Similarly on the right, 12 in parallel 4 will give me 3. Okay, so I'm going to redraw my circuit this way. So this is 2 ohm, this is 3 ohm. Okay, 4M here on the top, 4M here on the top, no change, copy and paste, right? 5 ohm, right? So plus on the left, minus on the right, okay? So following the same polarity here. And I'm going to label this as VO3, right? 3 indicates that this is the third source that I'm dealing with. Okay? Okay, so then what is the strategy here, right? So to find VO3, right, this is VO3. So what I'm going to do here is I'm going to, let's see, so over here I find, I first find the current and then I multiply by the resistor, right? That is a same sort of a strategy that we used earlier, right? So if you recall, if I know what is the current passing through this 5 ohm resistor, okay, this 5 ohm resistor, if I know the current passing through this 5 ohm resistor, then I can simply take that current, multiply by this 5 ohm resistor, I times R, to get the voltage. Okay, so that's exactly what I'm trying to do here. Okay, so how do you find the current? Well, that's straightforward, right? Because we know we can just use a current division. So we can first combine this 2 ohm and 3 ohm together because they are in series, right? So in other words, if I were to redraw my circuit, right, I'm going to sort of rotate it, okay? So this is 4M, right? 4M going up, okay? So it's like I rotate this entire circuit here 90-degree clockwise, okay? Clockwise, right? Okay, so this is 5 ohm, Okay, plus here, minus here, and label this as VO3. Okay, this resistor on the left is simply 3 plus 2, right? So this is also 5 ohm. Okay, so since I have two branches, okay, or two paths with equal resistance, so I know that half of this current is going to go into this 5 ohm and the other half is going to go into the other 5 ohm resistor, right? It's an equal split. So 2M and 2M, okay? So, and even without doing current division, right, you can kind of eyeball it, right? But, you know, more formally, we'll say 4M, okay, multiplied by 5 on the top, okay, divided by the sum. Okay, so you get 2M, right? So from here, you get 2M. So 2 times 5, right? So if I know that 2M is going into this 5 ohm, and then another 2M is going to the other 5 ohm, then I know that 2 times 5 will give you 10 volts, right? So it's a Ohm's law, right? So I times R is equal to the voltage. Okay, so 2 times 5 will give you 10. Okay, so that's how I get this 10 volts for my VO3. Okay, and then of course, you know, the last step, which is very, very important, is you need to know how to sum all these contributions up, right? Because, you know, you have done 90% of the work, right? You step through all three sources, but then, you know, the very last step is critical because you need to sum up linearly, sum or add all these three contributions. So you sum up VO1, VO2, and VO3. So you have 4 plus negative 14.25 plus 10, and that will give you negative 0.25 volts.